So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are gonna talk about the proof of this amazing result, actually, or relation or representation of e to the x. Well, similarly, like this, we know about the Taylor expansion of e to the x, right? That is this one. Well, yeah, we will talk about the proof of this one also later on, but for now let's consider this one. And you know what, I have used this result multiple times in my past videos, but I've never talked about the proof of this one actually. And let me show you the proof here. So 4 weeks ago I've uploaded a video in which I have proved this crazy looking relation that is known as the Euler's reflection formula, right? And I have pasted this image like beside of this relation, because I have used this relation to prove this one down, right? But you know what, I haven't talked about the proof of this one in that video. So that is why I need to just talk about the proof of that, because I don't want you to just memorize all the stuffs, right? And you know what, there was some problem here, that is, it's not t tends to infinity, but it was n tends to infinity. So yeah, I just want you to correct that down if you're feeling something wrong about that, right? Well, it is wrong, obviously. So this is my like screenshot of my YouTube channel's page actually, and I just wanted to show you that I just used this relation down to prove the Euler's reflection formula. Although I have done the proof of Euler's reflection formula with another method, so you can just check that out with just clicking on the playlist, and you can see the Euler's reflection formula. I think I have uploaded 2 videos on that. So yeah, you can just check that out if you want. But now let's talk about the proof of this one actually, right? Let me just get rid of this one. Oh, I'm sorry. Oh wait, yeah, it's fine. Okay, so basically we just have to prove this limit equals to e to the x, right? So let's talk about the limit. Let L equals this limit, right? Yeah, okay, I'm sorry, actually someone just called me out of nowhere, so I just have to just pick up that call. I'm sorry about that, but yeah, it's all right. Okay, so yeah, we were on just letting this limit equals L, that is limit n tends to infinity of 1 plus x over n to the n, right? Okay, now like this n is just bothering us, I think. So to get rid of that, we just have to take natural logarithm both sides. So taking ln both side, actually natural logarithm both sides, so that's gonna give us ln of L equals ln of this limit, that is limit n tends to infinity of 1 plus x over n whole to the n. Since ln is a continuous function, so we can just switch the order of these two things. So basically it is ln of L equals limit n tends to infinity. And if we talk about this one, so actually when we talk about the ln of this one, so this n would be just come up in front of the ln, and this argument would be the same, right? Basically this is going to be happening. Yeah, it's fine. Okay, so finally we just got rid of this n, and we are having a simple closed form of this. So in order to just use the L'Hopital rule here, so just let me just write that down. In order to use L'Hopital rule here, we just have to do some changes, like in this part actually. Let's just do that right away. So it's ln of L equals limit n tends to infinity, and well, we can write this as ln of 1 plus x over n actually, right? Wait a second. Yeah, it's fine. X over n over, we can write that n with like this way. So basically when we just solve it, so we're gonna have the same result that we had earlier, like that. Now we have we have this function on the numerator, and we have this function in the denominator. So we are just going to take the derivative of those functions separately, because L'Hopital rule says that right? So let's talk about the derivative of the numerator, that is d over dn of ln of 1 plus x over n. Be careful guys, we don't gotta go for the derivative with respect to x, but we are taking the derivative of ln of 1 plus x over n with respect to n, so don't get confused about that. So if we take the derivative, so it's 1 over 1 plus x over n, and with the chain rule we can say that it's x times the derivative of this 1 over n, that is negative of 1 over n squared, right? Okay, so basically numerator comes out to be negative x over n squared over 1 plus x over n, right? So let me just cover it in something like this parenthesis, right? Next, if we talk about the denominator right over here, so it's quite easy. D over dn, we had 1 over n here, right? So if we take the derivative of that, so we're gonna have negative 1 over n squared. And now we just gotta go and substitute these two values here. Let me just cover it in a bracket here also. So yeah, it's fine, in a box actually, not a bracket. So we gotta go and substitute this one over here and this one over here. So we are having ln of L equals limit n tends to infinity of negative x over n squared over 1 plus x over n, and whole over, actually it's negative 1 over n squared. I hope you are clear with that, right? Okay, now if we simplify this, so you know what, this can be written as negative x times, oh I'm sorry, let's not consider this negative, but we can write this as x times negative 1 over n squared, and this negative 1 over n squared cancels out with the denominator 1. So we're gonna have ln of L equals limit n tends to infinity of, so yeah. Okay, and next we got just rid of this one and this one actually with a negative sign as well. So we're gonna have x over 1 plus x over n, and you know what, when when n tends to infinity, so that means x over n tends to 0, right? So basically this part is going to be 0 along with this one. So finally we are having ln of L equals x over 1 plus 0, that is x. So basically we are having ln of L equals x, and now taking e both sides, something like this. So we're gonna get rid of this ln here, as you might know about that. So we are having L equals e to the x, and hence guys, that we assumed earlier, the limit that we have begun with, this equals this one. So let me just write down that limit along with the representation of e to the x, like that. So it's limit n tends to infinity of 1 plus x over n to the n. And yeah, that was really amazing guys. And you know what, I thought that it would need a lot of things to be proven, but yeah, it was quite simple, and it's literally simple, and it can be proven, I think, by a 11th grade student also. So yeah, it's not that difficult to be proven, but I thought that actually I have never seen any kind of proof on YouTube's like of this relation. So that's why I just thought that it's quite difficult to prove. But when I got to just involve in it, I was like, wow, it's quite easy, and it's easy, and let me just share it with you, right? Okay, so yeah, thank you so much for watching this video guys. If you got to learn something from this video, so just make sure to like, subscribe and share. And again, if you got any kind of doubt or anything wrong, so please just it's your responsibility to catch me up and just tell me that Aman, you are wrong here, you just have to correct that down right away. And I would just say, I'm sorry guys, I just made an error over there, so please correct that down by your own. Okay, so yeah, thank you so much for watching this video guys. And I'm in the progress of that third part of proving the all 6 integrals. So it will be uploaded soon, so just stay tuned for that video. And yeah, you got to learn a lot of things, I think. So yeah, thank you so much, and thank you so much, and goodbye, take care, and be safe.